All right, the purpose of this video is to get you guys a little bit of a head start in Chapter 8. Lewis structures are a huge part of Chapter 8, and we're going to walk through how they're done in this video. So the first thing to understand is what a Lewis structure is, and it's a structural representation of a molecule. So it will tell you where the double bonds are located, where all the extra valence electrons are located. It gives you more information than just the formula itself. The first thing we have to keep in mind when we're doing Lewis structures is the octet rule, which states that atoms tend to gain or lose electrons in order to attain a full valence shell of 8 electrons. To give you a visual on that, if you think about, for instance, bromine, okay? Bromine is found in the 4th shell. And so if you wanted to do its final row of electron configuration, you would start with 4s2, and then you would go through 3d10, and then 4p, 1, 2, 3, 4, 5. So the 2 over here were 4s, and these 5 over here are 4p. So 4s's and 4p's, these are going to be the outer shell, and remember this middle section here was the 3Ds. And so that's technically not part of bromine's outermost shell, because the outermost shell is going to be the 4th shell. So if you look at bromine, it's got 1, 2, 3, 4, 5, 6, 7 electrons in its outer shell. It only needs one more to complete its octet to have its full outer shell of 8. And so it only needs to gain one more electron. Okay? So that's what we're talking about when we're talking about the octet. The only elements that do not need an octet to be quote-unquote completed is hydrogen and helium, and that's because they're in the first row, and the first row can only hold 2 electrons, and so once they've got 2, they're good to go. Okay? So anyway, that's the octet rule, and that's what we follow for doing Lewis structures. The next thing we need to know is how to do Lewis dots for single elements. It's pretty simple. However many valence electrons it has, you put 1 dot on it. So if you look at sodium, it has 1 valence electron, so you put 1 dot on it. Magnesium has 2 valence electrons, you put 2 dots on it. Oxygen has 6, and chlorine has 7. If you can see, I'm trying to kind of obey like a 4-side rule where there's like a top, bottom, left, and right side, just to kind of give myself a little bit of organization where I'm putting these elements or these electrons. If you don't remember again how to find number of valence electrons, you just count across the periodic table, skipping the D's section. So for arsenic, if you wanted to figure out how many valence electrons it has, you go 1, 2, skip the D's, 3, 4, 5. Okay, so just keep that in mind. All right, so that's Lewis dots for single elements. Lewis structures, when we do Lewis structures, again, the whole point of doing Lewis structures is to complete elements octets in order to have a complete full outer shell of 8. So if we wanted to do the Lewis structure for water, for instance, what we would do is just draw out the elements as they exist with the single elements. So we've got our electron, 1 electron on hydrogen, 1 on this hydrogen, and then 6 on the O over here. When you draw a line, that represents electrons being shared between the 2 elements. So when I connect those 2 electrons, that means now this hydrogen has the 1 electron that came from itself, and now it's sharing this 1 other electron from oxygen. Okay? Likewise, this oxygen now has this 1 electron that came from itself, and it's sharing the electron that comes from hydrogen. Okay? And I can do the same thing over here. And so if you count total shared electrons, this bond now represents 2 shared electrons, or 2 total electrons, 1 from oxygen, 1 from hydrogen. So 2 total electrons on hydrogen, and this is 2 on this hydrogen. And then if you count what's on the oxygen, we've got 1, 2, 3, 4, and then 5, 6, 7, 8. Okay, so the oxygen has completed its octet, and the hydrogen is basically containing as much as it can hold, because remember, hydrogen is in that first row. Okay, so when I'm counting, again, I'm counting the electrons belonging to the element itself and the shared electrons. So that's why I'm counting this as 2 for each one, because there's 2 electrons in that bond. So 2, 4, 6, 8, that's how many electrons are on oxygen right now. Okay, so we know the structure is done because the octet is completed for oxygen, and hydrogen has as many as it can hold. So there's a pretty short method that I use in order to make Lewis structures that makes life pretty easy. And it follows a series of steps. So here are the steps for drawing Lewis structures. The first thing you want to do is identify what the central atom is going to be in your Lewis structure. So usually it's the element that you only have one of. So in this case it will be the carbon, in this case it would be the nitrogen, and in this case it would be the oxygen. So basically look out for whatever element you only have one thing of, and then surround the rest of them with the extra elements. The next thing you want to do is draw single lines attaching the outer elements to the central ones. Step 3, fill in the valence electrons on all the atoms. And step 4, create more bonds to create the octet for all of the atoms. And I know this doesn't make a whole lot of sense just written out like this, so we're going to walk through a few examples, okay? And again, you guys can pause this video at any time in order to write down your notes, okay? So, keeping in mind these 4 steps, let's take a look at a couple examples. So, looking at, let's see, PCl3 is our first example. Okay, so PCl3 is what we're writing. Okay, so in this case, phosphorus is going to be our central atom, so I'm going to put that in the middle. Chlorine is going to be on the outside, so I'm going to draw single lines connecting my outer elements. So I've got 3 chlorines. Okay, that was steps 1 and 2. Now I fill in the valence electrons on all atoms. So in phosphorus, I can look at the periodic table and it tells me that I have 5 valence electrons on phosphorus. Now remember, each one of these lines represents 1 electron coming from phosphorus and 1 electron coming from chlorine that we then connected to make a bond. So this line represents 1 electron coming from phosphorus, and so does this one, and so does this one. So we've got 3 electrons occupied coming from phosphorus to make bonds. So if we're using 3 to make bonds, and there's 5 valence electrons on phosphorus, that means I have 2 left over. So I'm going to draw 2 dots on phosphorus up here. So now I've got my 1, 2, 3, 4, 5 valence electrons on phosphorus, all accounted for. And now we go back over to chlorine. There's 1 electron occupied in a bond right now on chlorine. Chlorine has a total of 7 valence electrons, so I'm going to draw in the remaining. So this counts as 1. So 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And again, these are, I'm just counting the electrons coming from the individual atoms, okay? So now that I've got all that done, I've drawn my lines, I've completed whatever valence electrons need to be included. And now I can evaluate for the octets. So when you're evaluating to see if there's an octet on an atom, you want to count total shared electrons as well. So remember, each of these lines represents 2 electrons, 1 coming from phosphorus, 1 coming from chlorine. So if we're including the shared electrons, phosphorus has 1, 2 up top, 3, 4, 5, 6, 7, 8. So phosphorus has a complete octet. Chlorine has 1, 2 in the bond, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So I've completed the octet for all of my elements already, and so this is a complete Lewis structure. So this is the done, finished, complete Lewis structure for PCl3. Okay, so pretty straightforward. Some of these are actually going to be that easy. Otherwise, it takes a little bit more work, so let's move on to another example. Let's see. Sometimes a formula will be more than just 2 different elements. Here's our second example. We'll use CH2Cl2. Okay, so sometimes people get a little tripped up on this, but take a look. There is only 1 element that is single, the rest are doubled. So that tells us carbon is going to be our central atom. And so we identify our central atom, and then we draw single lines connecting the other elements. In this case, the order isn't going to matter. I'm just going to put my H's here and my Cl's here. It doesn't really matter what sides I put them on, but I've connected my elements. And now my next step is to write in any valence electrons I have left over. Carbon has 4 valence electrons, but if you take a note, there are 4 bonds being made to carbon. So that means all of carbon's 4 electrons are participating in bonds right now. So it's good to go. Hydrogen has 1 valence electron and it's participating in bond. So we're good to go there. And then chlorine has 7 valence electrons. 1 is participating in bonding. So 2, 3, 4, 5, 6, 7. 1 from here. 2, 3, 4, 5, 6, 7. Okay, so that's the next step there, was to fill in the extra valence electrons. Now we evaluate for the octets. So for carbon, including shared electrons, 1 coming from hydrogen, 1 coming from carbon, we have 2 in this bond, 2 in that bond, 2 in this bond, and 2 in that bond. So that's 8 complete shared electrons, so we're good to go on carbon. Hydrogen is good to go with 2, and chlorine, 2, 4, 6, 8, 2, 4, 6, 8. We're good to go on the chlorine as well. Okay, so good to go on this structure. Let's go for something that's a little bit more difficult. All right, so we're going to do HCN. Okay, in this case, there's only 1 of every single element, so what we're going to do is just draw them in a line the way they're written. So H bonding to C, bonding to N. Okay, that's what you do when they are just all single elements. Keep in mind also, remember, hydrogen only has how many valence electrons? 1 valence electron. So, could we ever do this? The answer is no, because hydrogen does not have 2 electrons to make bonds with. There's 1 electron coming here and 1 electron coming here. So this literally could never happen because hydrogen does not have 2 valence electrons to bond with. So never write it like that, never put hydrogen in the middle for that reason. Okay, so we have drawn our single lines. Now we need to write dots in for the remaining valence electrons. Carbon has 4 valence electrons. Right now there's 1 occupied in bonding here and 1 occupied in bonding there. So I'm just going to draw in the 2 remaining there. Okay. Nitrogen has 5 valence electrons. There's 1 occupied in bonding here. So we're going to draw in the rest of its 5. So 1, 2, 3, 4, 5. I kind of like things to be symmetrical, so that's why I draw it like that. Okay, so now we can evaluate for the octet. Hydrogen has 2, including shared electrons, but that's good to go. Hydrogen can only take 2. Carbon has 2, 4, 6. Okay, 2 coming from here, 2 coming from here, and then 2 on itself, so it's not good. It's only got 6, and then nitrogen has 2, 4, 6 as well. So we're not completely done yet. At this point, we can make some new bonds. So what I'm going to do is take this electron and this electron and make a bond out of them. So I'm just basically going to make them into that bond there. So now reevaluating, I have 2, 4, 6, 7, and 2, 4, 6, 7. So now everybody has 7. I'm going to make another bond, erase that dot and erase that dot, make it into a bond. And let's see, 2, 4, 6, 8 on carbon, that's good. And then 2, 4, 6, 8 on nitrogen, that's good to go. So this is our final structure for HCN. Okay, one more, let's see, let's do a tricky one. I hope you guys are kind of getting the method. There's another thing I want to point out to you guys. When you have a compound with a charge, okay, so BrO3 minus. This minus charge tells us that there is an extra electron somewhere floating around in the structure, okay? So we're going to keep that in mind when it comes to making our octets. So we're going to follow the same methods we did before. So bromine's got to be the central atom here. So Br, and then we have 3 oxygens, so 1, 2, 3. Okay, now we can draw in our extra electrons. Bromine has 7. Right now 3 are occupied in bonding, so that means we have 1, 2, 3, 4 left over, okay, because 4 plus 3 equals 7. Oxygen has 6 valence electrons. Right now there's 1 occupied in bonding, so that's 1, 2, 3, 4, 5, 6, and the same goes here. 1, 2, 3, 4, 5, 6, and the same goes here. 1, 2, 3, 4, 5, 6. Okay, So evaluating for our octets, we've got 2, 4, 6, 8, 10 on bromine. We've got 2, 4, 6, 7 on oxygen. 2, 4, 6, 7, 2, 4, 6, 7. So all the oxygens have 7. Bromine has 10 right now. I do want to point out something to you guys. If you see where bromine's located on the periodic table, it's in, oh, this is so shiny. It's in the 4th row, okay? So remember, the 4th shell has a d orbital, the 4 Ds, available to it. So if bromine needs to hold on to extra electrons, it technically does have the 4d orbital to hold on to those extra electrons, which is why it's okay for bromine to have 10 electrons. Okay? We want to avoid overloading electrons if we can, but it's permitted for bromine to have 10 because it has the d orbital available to it. So the 4d orbital is there. You could not put 10 on something like fluorine, because fluorine is in the 2nd row, and we know that the 2nd row does not have a d orbital, so it's not possible for fluorine to have 10 in its outer shell because there's no 2 Ds. Okay, so just keep in mind everything 3rd shell and below can hold more than 10 because they have d orbitals. Okay, all right, so taking a look at what we can do, I am going to take one of these electrons from bromine and this extra electron on oxygen, and I'm going to make a bond. What this does is complete the octet for oxygen. It goes 2, 4, 6, 8. So now my oxygen is complete. And I've got another extra electron here, so I can get rid of that guy, and I can get rid of this guy and make another bond. So now I have 2, 4, 6, 8 on oxygen. And here's something we could do, okay? This is one option. Remember, we've got this extra electron up here. So right now we have a freebie electron that we could put anywhere we want. So what I'm going to do is take that extra electron, and I'm going to stick that guy right here. Okay, I'm going to throw that on our oxygen. So now this oxygen has 2, 4, 6, 8 total shared electrons, and so its octet is complete. And then rechecking our bromine, we've got 2, 4, 6, 8, 10, 12 electrons on bromine, but again, it's got extra space so it can hold that. So I'm going to call this structure good to go, and the last thing you need to do when you're drawing a structure that has a charge is put it in brackets. So this whole thing is going to go in brackets with a negative charge out top. That negative charge tells me that somewhere in my structure I have an extra electron floating around. Okay? I want to point out something to you guys. There was another way that you could have done this structure, and it's going to look like this. Okay, I'm going to leave this one put together for a second so we can compare. So BrO3 minus, this is the other way that you could have done the structure. Let's draw our Br in the middle, 3 O's, drawing in our extra electrons like we had before. So far everything is the same as the previous structure. Okay, this is where we were before, and remember what we did was we took one electron from this pair and that electron, and we made a bond. And then we did the same thing down here, so we take this electron away, make that electron go away, and make this bond. And here's our last option. What we also could have done is remove this, like one of these 2 electrons, and that electron, and made a 3rd double bond, and then used this extra electron and just stuck it on bromine down here instead. Okay, this technically is a correct structure because all of the oxygens have an octet. We've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and bromine has 2, 4, 6, 8, 10, 12, 14 electrons on it. Okay, so that's what I want to point out to you. The bromine in this situation has 14 electrons hanging out on it. Okay, versus this, oh, and I forgot my brackets. Okay, contrasting that with this structure that we made previously, this bromine structure has 2, 4, 6, 8, 10, 12 electrons on it. Okay, now remember, the electrons have negative charges and they're going to try and repel each other as much as possible. And so you want to avoid overloading the central atom if you can. So if you have to pick between 2 different structures, 12 electrons on one central atom or 14 electrons on one central atom, you want to pick the one that puts fewer electrons on the central atom, okay? This will further distribute the electrons throughout the structure, and I can show you guys a little bit later in class. There's a way we can evaluate these structures using formal charges that will also prove this theory, okay? So if you have an option between placing double bonds or putting extra electrons on the outer elements, that's what you're going to want to do. If you have extra electrons, 9 times out of 10, they're going to end up on an outer atom. Okay, so I think that's a good place to start. I'm going to give you guys some homework in class today to work on this stuff, but for now, that's all.